Bienvenidos, Hushamdi, and happy holidays, and welcome to this HUD 8 techtorial on the new Cisco Networking Academy Enterprise Networking Security and Automation course for CCNA version 7. In this techtorial, we're going to be taking a look at Packet Tracer Activity 2.3.11, where we're going to do a deep dive into determining the DR and the BDR. So what are you going to learn in this techtorial? Well, we're going to be covering how you would see who the current DR and BDR routers are. We're going to talk about why we need to have a DR and a BDR. Again, it's great to know the commands that you need to use to configure the DR and the BDR and to validate the DR and the BDR. But why didn't we have a DR and a BDR in our previous video where we were looking at OSPF in point-to-point single area networks? However, here in this multi-access network, we are going to have a DR and a BDR. And so you should be asking yourself, why is that? Why do we need the DR and the BDR? We're going to be talking about the multicast addresses that are used for OSPF and the DR and the BDR, 224.0.0.5 and 224.0.0.6. We're going to talk about the OSPF router ID. Again, that critical value. Think of it as a fingerprint that uniquely identifies that OSPF router in the OSPF shortest path first graph. Now, we're also going to be talking about how that router ID is selected. And we're going to look at the IP OSPF priority command, where we can control which router would become the DR and which router would become the BDR. Now, in addition to this, I'm going to add some additional value in here. If you're familiar with my tutorials, you know that I'd like to go just a little bit deeper than the activity in order to make sure that you have a better understanding of exactly what the technology is all about. Because there are some semantics that come into play when we talk about the DR and the BDR election. And what happens if we already have a designated router and a backup designated router, but a router with a superior OSPF priority configured on its interface, or a router with a superior router OSPF router ID comes into the OSPF domain? What happens? Is it preemptive or is it not preemptive? And if not, why not? And those are just some of the things that we're going to be talking about in this video. Again, really excited for the new Packet Tracer version 7.3 and the new activities that are part of the ENSA CCNAv7 curriculum. So, the first thing I want to talk about is let's address the question, why is there a DR and why is there a BDR? Well, for that, we're going to get into what I like to call the Wayback Machine. Now, this is a page from the authoritative primary source text on OSPF. It's called Anatomy of a Routing Protocol. It's written by John T. Moy. And I'm going to pull the RFC for OSPF up here in a second. The RFC is the request for comment. It's the standardization document that is put together at the Internet Engineering Task Force, or the IETF, that details how you would go about implementing OSPF. And that is also written by John T. Moy, and only by John T. Moy. So, if we take a look at John T. Moy's own words right here, he said, at the same time that we were developing OSPF for TCP/IP, the ISO standards organizations were developing a link state routing protocol called IS to IS for the OSI protocol stack. Now, you probably remember this from your early CCNA studies. The emerging IS to IS protocol had already developed an efficient mechanism for running a link state protocol over broadcast links. Remember, in my previous video and my Packet Tracer tutorial that covered OSPF on point-to-point links, there is no DR BDR election on a point-to-point link because by definition, a point-to-point link will only ever have two nodes on that link, one on one point and the other at the other point. So we don't need the DR and the BDR. But when we're talking about broadcast links, and when OSPF was originally created, the point-to-point link was the predominant link in use way back in the Stone Ages. However, as Ethernet began to catch on and TCP/IP began to get traction, we had this new thing called an Ethernet LAN, or local area network. And when we have a local area network, we have more than two routers that are communicating with each other. And so this is the reason why we have the designated router and the backup designated router. And what Moy is saying right here is they looked at what the ISO was doing with the OSI protocol stack and the IS to IS routing protocol. And they had what IS to IS and the ISO and what OSI refers to as a pseudo node. Well, Moy simply looked at what they were doing and said, hey, that's a great idea. We need something like that for the link state routing protocol that we have called OSPF, and I'm going to call it a designated router. And that is exactly what Moy did. In fact, if I was to sneak up here to page number 53, this explains why on a multi-access broadcast segment like Ethernet, why we need the DR and the BDR. And let me pull my pen out here to highlight a few things. You've probably seen this equation, right? The n times n minus 1 divided by 2. Because on a multi-access segment like Ethernet, if this is my switch, and I have a router here, and a router here, and a router here, and a router here, OSPF would say that this router needs to be adjacent with those routers. This router needs to be adjacent with all the other routers. And you can see that this is going to get very messy rather quickly with the number of adjacencies. Excuse me, a full mesh would require for all of these routers to become adjacent fully with all other routers. And that's where that equation comes from, the n times n minus 1 divided by 2. And Moy realized very early on that this costs too much in terms of the amount of flooding traffic that would be sent over the LAN. And if you think about it, it makes a lot of sense. And so what Moy decided to do was, again, borrow the idea that the ISO was using for their link state routing protocol, IS to IS, and simply say, I'm going to have a designated router. And we have a backup designated router as well, but we're going to have a single designated router that is going to be the center of the universe, one router to rule them all, if you will. And that designated router is going to be responsible for not only receiving link state updates and the flooding of LSAs from other routers, but it's responsible for sending those updates out. It's the chosen router, right? The designated router. Now, the backup designated router is simply there as a standby in case the designated router fails. Now, a key takeaway here is that all routers are fully adjacent to the designated router. Even the BDR is fully adjacent with the designated router. And all routers in an OSPF environment that is on a multi-access broadcast segment like Ethernet, all other routers are also fully adjacent to the BDR. Because the backup designated router, again, it's there to give us continuity. It's there to give us consistency and reliability and redundancy. Because if the DR router were to fail, it will be the BDR router that's going to take over immediately, because it's already fully adjacent with all other routers. It's already fully synchronized from an OSPF link state database perspective with all other routers. And so that's why on a point-to-point link, we don't have a DR and a BDR, because there's no need. There are only ever going to be two routers on that point-to-point link, by definition. But when we transition to the activity we're going to be looking at, that is where we do have a DR and a BDR, because that equation, n times n minus 1 divided by 2, when we start to talk about a full mesh of adjacencies, can quickly get out of hand. Now, this is the John T. Moy book. I also wanted to show you the RFC, as well as the John T. Moy book and one other text. So the RFC, this is 100% free, right? You can see this is the internet standard for OSPF version 2. The only author here is John T. Moy. And if you were to go down to section 7.3, that is where you'll find the section on the designated router. So simply Google RFC 2328, and you can come down to section 3 and read about the designated router. And you'll find out why every broadcast, and we'll leave the NBMA out of the discussion right now, but there's another network type that we've talked about in the previous packet tracer tutorial, non-broadcast multi-access. Those network types will also have a designated router, but it goes over the role of the designated router. It talks about how it's elected using those hello packets that we talked about. Because as we get into the details here of how the DR is elected, we're going to find out that it's going to be based off some values that you would find in the hello packet. One of those values being the OSPF router ID. Again, a common thread in all OSPF conversations is going to be the router ID. That is the fingerprint that uniquely identifies that router. All right, excuse me. Let's go ahead and take a look at the book by John T. Moy. And this is commonly referred to as the blue OSPF book. There's another one that has an all yellow cover. That book is if you're trying to write an implementation in the C programming language. Probably not appropriate at the CCNA level, but this book here, if you've got the $17, this book is an amazing book written by John T. Moy. This is primary source material, just like the RFC is primary source material. It's written and authored by the inventor, the creator of OSPF. It doesn't get any better than that. Now, just short of that is the book that you see up here. This book is legend in the OSPF and IS to IS routing space. It's written by a gentleman by the name of Jeff Doyle. And he is a prolific author when it comes to routing protocols. His books on BGP are the definitive guides on BGP. And this book on OSPF and IS to IS is quite possibly the second best book, right behind Moy's book, and some people may argue even better. But again, if you don't have the resources to purchase these books, you can still look at the RFC, which is free. If you do have the resources to purchase these books, these are two books that are in any serious network engineer's library who is doing anything with routing protocols like OSPF and IS to IS. They are the two link state routing protocols, and they are the dominant interior gateway routing protocols across almost all environments and all vendors. All right, let's go ahead now and transition to the activity. Again, I wanted to add a little value there to your studies by talking about these additional resources that you can take a look at. So we've talked about the DR and the BDR, and we've talked about why we need to have them. Now let's go ahead and jump into this activity. You can see here, each of these routers has a loopback address. That loopback address has been selected as the OSPF router ID. Now, let's take a quick review here. How is the OSPF router ID selected? It's basically a three-step process. The first value that would be selected for the OSPF router ID would be the value that you manually configure on the router with the router ID command under the OSPF global configuration section. If you didn't do that, the second value or the second step would be that iOS is going to look and see what the highest IP address is on any loopback interface. If you've got a loopback interface like we do here, and you didn't manually set the OSPF router ID value in the OSPF global configuration section, the loopback address is going to be selected as the OSPF router ID value. If there are no loopback addresses and you didn't manually configure the OSPF router ID under the OSPF global configuration section, the third and final step would be to pick the highest IPv4 address off any active, meaning an up-up interface, and that would be your OSPF router ID value. So let's go ahead and dive into this activity now that we understand how the router ID is chosen, what values it uses, what the order of operations is in selecting the router ID. Let's now take a look and see what the DR and the BDR roles are for the routers here. So let's first come on to router A. I'm going to go from user exec, which is indicated by the greater than sign, to privilege exec. I'm going to say show IP OSPF neighbor. As we can see here, we've got some different values that we're going to be working with. First and foremost is the neighbor ID. Now, when you look at this, and I mentioned this in my previous tutorial, when you look at this value, it might become confusing sometimes because it takes the shape and the form of an IPv4 address. However, it doesn't have to be an IPv4 address. Remember, I can manually configure the OSPF router ID to any of the values. Well, not any. There's a couple that are reserved, or there's one specifically that's reserved that I'll talk about. But again, it looks like an IP that's on the router. But remember, it doesn't have to be an IP. So if you tried to ping this address and it wasn't a loopback and it wasn't on an up-up interface, and I had manually put it in as the router ID, you wouldn't be able to ping it. So remember that. Neighbor ID is router ID. The OSPF router ID. Now next is the priority value. Remember, we talked about the OSPF priority value. Where is it configured? It's configured on the interface on the router that's participating in the OSPF routing domain. And you can see the default value is 1 for broadcast multi-access segments like this, like Ethernet. If it shows anything other than 1 for an Ethernet interface, that means that something's manually been changed. And you can see here, router C, which is indicated by the 33, it was manually set to 2. In fact, if I was to clear the screen here, and we were to step over to router C, onto the CLI, and say, show run, and let's actually see if I can say show run interface gig 00, show run interface, sorry about that, show run interface gig 00, and we can't use that yet. And unfortunately, I wish that was a command that we had access to here in Packet Tracer because I wouldn't have to do this. You can see when we come down here, the OSPF priority has manually been set because whoever the administrator of this local area network was, they decided they wanted router C to be the designated router. And on router A, that is what we see right here. Remember, when you see the state, meaning it's fully adjacent, what's on the opposite side of the / is going to be the state of the other router, right? Of this router here, not the router on which I'm running this command. So this is telling me that router C, I am fully adjacent. The interface priority of router C that it's advertising is 2, and it is the DR. Because of the other routers that are here, it has the highest priority manually configured on its interface in the OSPF domain. We see what that IP address is on router C's interface that has the priority set to 2, and we see the interface out which we are learning about router C. So this is our local interface. This is router C's state, right? We are fully adjacent with router C, and it is the DR. And so this also shows me that router B is the backup designated router. Now let's take a look and see what router B sees. So on router B, we go to privilege exec, show IP OSPF neighbor. And I see here that on router B, it sees router C as the DR, right? Remember, there will only be one DR in this or on this segment, right? On this segment, there'll only be one DR, and there'll only be one BDR, meaning router A is the drother. And we talked about these statuses a little bit in the previous video, where here you would see DR or BDR or DROTHER, right? And those are, excuse me, those are the states of the neighbors that are reflected here in this output. Now, you might even see two-way DROTHER, and I'll talk about that in just a second, because right now we only have three routers here. We've got router A, router B, and router C. So one's going to be the DR, that's router C. One's going to be the BDR, and right now that's router B. And then if you're not the DR and you're not the BDR, you're simply a DROTHER, a DR other. Now, everybody's fully adjacent to the DR and the BDR. But if there were multiple DROTHERs, they're not fully adjacent with each other. And again, I'm going to add that in here toward the end of this activity. So we've taken a look at router A, we've taken a look at router B. Let's take a final look here at router C, just for completeness, show IP OSPF neighbor. And again, router C sees router A as the DROTHER, it sees router B as the backup designated router, and we are fully adjacent with all of those routers. So we've answered this question: which router is the DR? Router C. Which router is the BDR? Router B. What is the OSPF state of router A? Well, it's a DROTHER, right? A DR other, because it's not the DR and it's not the BDR. So now we're going to take a look at some debugs, and these are absolutely fantastic. So here on router A, let's say debug IP OSPF adjacency. Now, we're not going to see anything right away, debug IP OSPF adjacency, because there aren't any activities or events taking place that are disruptive, that would facilitate or result in a debug message coming to our screen. Now, we're about to make that happen here in step number 5. We're going to disable the Gigabit Ethernet 00 interface on router C. Now, you'll notice it says wait 30 seconds for the dead timers to expire. Well, let me go ahead and shut that interface down, and I'm going to talk about that for just a second here, because when we're dealing with point-to-point links, if I take one link down on one side of that point-to-point connection, the OSPF adjacency goes down immediately. And that's because it's picked up, that down interface is immediately sensed at layer 1 and layer 2. Because when you shut a point-to-point interface down on one side, it's immediately going to be seen on the other side. And we don't sit there for 30 seconds waiting, right? So that's why here, when I go into global config, interface gig 00, and I say shut, you'll notice router A and router B, where are the debug messages, right? Should there not be an event here? And the answer is not yet. There will be, but not yet. Because when I shut down that interface on router C, router A and router B are not directly connected to router C. In fact, I could have shut the switch interface down. And router A and router B right now think that everything is just fine. They're sending their OSPF hello packets every 10 seconds, and everything is great. Remember, it's not until the dead timer expires, and there it is, and that was what we were looking for. It's not until the dead timer expires. Remember that 40 seconds? And it's going to be less than 40, right? Because when I shut the interface down, maybe it was at 32 or 33. So I'm going to say approximately 40 seconds. So that dead timer has to expire because router A and router B have no layer 1 or layer 2 knowledge of what the state of router C is right now. All they know is I'm connected into this switch and my interface is up and everything is great. And I'm sending my hellos and I'm receiving hellos, so everything is great. It's not until, remember, 4 of those hello messages are missed to where router A and router B now say, hey, we haven't heard from router C. In that 40-second window, we are taking the adjacency down. And so that was a nice segue into what we're about to see here. If I scroll back up, you can see that here is where we turn the debugging on. Here is where the adjacency about 40 seconds later, right? Approximately 40 seconds later, it went from full to down. The dead timer expired. Now, we'll come down here a little further because now we see the debug messages that we were interested in. Router A, which is the router I'm on here, builds an LSA and sends that LSA out with its router ID. Because we're now going to have a DR BDR election. And this is one of the trick questions that you may run into in your certification or testing lifetime. And that is, what is elected first? Is it the BDR that's elected first, or is it the DR that is elected first? Remember, and you can see it right here. This is proof, right? I always like to say the proof is in the debug, because the debug is going to tell you exactly what's going on behind the curtain, behind the scenes. And I'm going to explain why, because when I first tell learners this, they scratch their heads and look at me and say, that can't be right. So, what is elected first, the DR or the BDR? Remember, the backup designated router is elected first. The BDR will be elected first before the DR. And the reason for that is for continuity and smoothness, seamlessness in the transition from a BDR to a DR. Because I want you to think about this. If the DR got elected first, and this was a preemptive process of some kind, you would have the DR getting changed out, right? And, excuse me. And so when the new DR got elected, if it wasn't the backup designated router, it wouldn't be fully synchronized with all of the other OSPF routers. And so what would it have to do? It would have to synchronize its OSPF link state database. And depending on the size of your network, that might take some time. Time during which traffic is black holing in your network. While OSPF is converging, traffic is going to be dropping somewhere. And so this is one of the fail-safes that OSPF has designed in. The DR BDR election is not a preemptive process. And what that means is, if I'm the DR, right? Router C was the DR. And let me pull this back here. So router C was the DR. Router B was the BDR. And what that means is, if I added a new router here, and let's say I set the priority right here, the number one criteria in determining the OSPF designated router and backup designated router is this priority value right here. If I set this priority value here to the highest possible value of 255, and I bring router X online, and it joins this OSPF segment here in this OSPF routing domain, router C is going to remain the DR. Router B is going to remain the BDR. Now, in the scenario that we just had, let's say before I'm going to shut the interface down here like I did, but let's say before I shut the interface down, router C is the DR, router B is the BDR. This router X here exists in our environment as just basically, I brought them on as a drother, right? After the fact. And the DR goes down. The reason the BDR is elected first is because if we didn't have a BDR, we would want to elect the BDR. But since we have the BDR, it would immediately transition to the DR, right? Whoops, sorry, it's a bad R there. This is going to transition to the DR. This router here is not going to preempt the existing BDR and say, oh, I'm now the new DR. So it checks to see if there's a BDR first. If there is, the BDR is going to be your DR. And then we would have an election between the remaining routers, router X and router A, based off first their priority value on their interface. If that's not configured and they're both the default of 1, then it goes to the router ID value, which is the ultimate tiebreaker in determining who the DR and the BDR are going to be. when an election is first taking place. And so these guys, router A and router X, would compete to become the BDR, and router X would win that election. But it is not preempting router B from becoming the DR, because we're assuming here that if we have a BDR, it already has all of the link state database information and is already fully adjacent with all other OSPF routers. We don't want to select router X because we don't want to wait for router X to synchronize its link state database and become fully adjacent with all of the other OSPF routers. And we're going to see that as we walk through this process here. So we waited our 30 seconds. Let me get control of the mouse back. And we see that the BDR election, that's already been done. It's router B is the BDR. And so then router B transitions to the DR. And we see this final message here that the DR is now router B, and the backup designated router was router B. But wait, something else is going to happen, right? We've got this election that's going to take place for the BDR slot again, because now we don't have a BDR. Router B has become the DR and is no longer the BDR. And so the DR gets elected as router B. We elect router A as the BDR. And then you can see here in the final output, the DR is router B. The backup designated router is router A. And another way that we can see that in a great command is show IP OSPF interface, and for the specific interface that's participating in the OSPF routing domain. And here's router A's view of the network. The designated router is router B, and that is the router B's router ID. Here's the interface address for router B that is participating in the OSPF routing domain. And then the backup designated router is me, router A. And I'm saying me because I'm on router A. All right, so according to the debug output, which router was elected as the DR? It's going to be the BDR. And who became the BDR? Well, that's obvious. The only other router that's there that's participating, and that would be router A. So if I scroll down a little bit further here, we look at step 5. So now we're going to restore the gigabit Ethernet interface on router C. And here's where we need to talk about preemption. Because my question to you is, when we bring router C back online, and let me actually kick this off before I start talking, because we're going to be waiting for spanning tree here. You see the little orange dot. Spanning tree is going to go through the listening, the learning, and the forwarding, get us to the forwarding state. And while that's happening, let's talk about preemption and why this is a critical concept in the DR BDR election process. Now, remember, router B is the current DR. And we saw that. Router A is my BDR. But now I'm bringing router C. Remember, the former designated router, the router formerly known as the DR, is being brought back online. And we already know that on its interface, it has the OSPF priority value of 2, which is greater than the value of 1 that is on router A and B, the default value of 1. So this was configured. So the question is, do we allow router C to preempt the current DR and become the new designated router? And if you're thinking logically here, you're probably saying, well, wait a minute, if that happens, that would be disruptive, because now we've got this new designated router. And let's briefly highlight what the designated router is responsible for. When the flooding of LSAs is taking place, right? And that's those link state advertisements that are floating around the OSPF network. When LSAs are flooded, and I'll bring router X back in, we'll use this as an example. Let's say router X adds in a new network over here. We would have an LSA that gets flooded out. That LSA is flooded to the 224.0.0.6. That's the all DR routers address, right? And the only routers that are listening on that address are the DR and the BDR. So an LSA comes out advertising a new network here behind router X. It goes to the BDR and it goes to the DR because they are listening to 224.0.0.6. But what happens next is what's critical. The DR, and only the DR, then sends that link state update out to the 224.0.0.5, the all OSPF routers address. And the reason it multicasts that advertisement out to all OSPF routers is because if we had other routers out here that are not the DR and not the BDR, they need to learn about this new network so that they can update their link state database. And that is how this process takes place. So router X sends his LSA advertisement to the DR and the BDR via that multicast address 224.0.0.6. And then the designated router, and only the designated router, the one router to rule them all, then notifies everyone in this OSPF routing domain here of that link state advertisement or that link state update that, hey, there's a new network. So back to why we don't let router C preempt the DR is because if there's updates going back and forth to the DR and the DR is sending updates back out to everybody else, do we want to interrupt that with a disruptive preemption of the current DR? And the answer is no. And so when we take a look at the topology now that we've brought router C back online, let me get on to router C. And let's go ahead and say, show IP OSPF neighbor, again, phenomenal command to get a view of your environment. So router C has been brought back online. It has a superior OSPF priority configured on its gigabit Ethernet 00 interface. But router B is still the designated router. And router A is still the backup designated router. Router C is not going to preempt either of those routers and take their role over because they are already established. So there is no preemption here. And again, I'm stressing because they have already been elected as the DR and the BDR. If I was to turn all of these routers off and then turn them all back on right now, then yes, router C would be the DR, router B would become your BDR, and router A would go back to the DROTHERS state. But the state of router A and router B and the DR BDR election process has already taken place. And what that means is that all new routers that get added in are going to become DROTHERS. It won't be until we have some sort of disruptive event take place that we'll reevaluate who should be the new DR if in fact the DR crashes, or if the BDR crashes, who should be the new BDR in this configuration. So on router C, we saw that there is no preemption here. Now let's move to step number 6. We're going to disable the gig 00 interface on router B because it's here that we're going to see, and let me do that right now. It's here that we're going to see interface gig 00, and I say shut, and you can see we've got the red arrows here. This is where we'll see what happens when router C with a superior priority value set on its interface and router A with an inferior priority set, but router A is already the BDR. What's going to happen now? And so we're going to wait for 30 seconds, but I'm going to tell you while this is taking place. It says, according to the debug output on router A, which router was elected as the DR and which is the BDR. And so let's go over to router A because we should see that in that 30-second window, and there we go, we just caught it at the tail end here. So we've got an election that's going to take place. And the first thing we elect is the BDR. The backup designated router is elected first. Now, we elect the DR, and the DR is going to be router A. And you can see right here, DR, router A, backup designated router became router C. And the reason we elect the BDR first is because if there's already a BDR, that is going to be your new DR, irrespective of the fact that router C has a superior OSPF router ID and a superior OSPF priority value set on its gig 00 interface. It doesn't matter. It is not going to preempt the current backup designated router, because remember, that backup designated router is already fully adjacent with all other OSPF routers. It already has a fully synchronized link state database. It's ready to become the designated router. That's why we elect the new backup designated router first, and the current backup designated router is promoted to the DR. Now, step 7, restore the gig 00 interface on router B. And the major question is going to be, since the DR is now router A and the BDR is now router C, when we restore the gig 00 interface on router B, what exactly is going to happen? Now, if it follows suit with everything else we've seen so far, router B should simply just bring himself back online and become a DR other, but let's find out if that's actually what happens. If I go to interface gigabit Ethernet 00 and I say no shut. Now this is going to bring the interface back online. So we've re-enabled the link between router B and the switch. We're going to wait for the new BDR BDR elections to occur. And the question is, will the DR and the BDR roles change? Because remember, router C is the current backup designated router, but it has a superior priority value, and the priority value is the #1 indicator as to who should be the DR and the BDR. Router B and router A have the same priority value of 1, but router B has a superior OSPF router ID that ends in 22 as opposed to router A that ends in 11. But remember, A is currently the DR. C is currently the backup designated router, and take a look at what you see, right? And this is exactly what we would expect to see. Remember, I'm saying there's no preemption once the DR BDR roles have been defined. There is no preemption of those roles unless the DR or the BDR goes down and we have to hold an election for that backup designated router role. All right, so what is the status of router C now? Well, that's a great question. And router C is still our BDR. So let's say show IP OSPF neighbor. We can see it right above there, but let's say show IP OSPF neighbor. And router B is our druther. Router C is the BDR. Now, let's turn debugging off here on router A. We're going to say uall, which stands for undebug all. It's a shortcut way to get that command in there. And we'll just say end uall and turn debugging off there. And what we're going to do now is we're going to modify the OSPF priority, and we're going to force an election to take place. So we're right now, our completion percentage is at 0%. I'm assuming we're going to put this in, and this may bring us to 100%. We'll see what happens here. So let's go ahead and change the DR and the BDR priorities on routers A, B, and C. So we're going to come on to router A, and I'm going to say interface gigabit Ethernet 00, IP OSPF priority, and A is going to be 200. And yeah, that gives us a 33% right there. I'm going to write mem and save my config. We'll come to router B, where we're going to go into global config, interface gigabit Ethernet 00, IP OSPF priority on router B is going to be 100. And let's save our config there. And on router C, we're going to go ahead, and there's two ways that we could do this, right? So on router C, if I say show run, and we look at the interface gigabit Ethernet 0, you can see the command is IP OSPF priority 2. So what would happen if I came in here into gig 00 and I said IP OSPF priority 1, and then I said do show run? Are we going to see displayed under the interface an OSPF priority of 1, or is it going to be gone? And you can see right here, there's nothing listed here for the IP OSPF priority. Now, if you're new to Cisco and you're going down the CCNA path, and you're going to go beyond the CCNA, this is a very important point to remember. 99% of the time, the default value, when set, will not show up on the interface. And it's true on routers just as it's true on switches. If you were to turn port security on and say and if you were to say, port security maximum 1, right? That's the maximum number of MAC addresses by default. So if you set that, it's not going to show up. If you said port security shutdown mode, right, for the port, if there's a port security violation shutdown, that's the default. That is not going to show up in the running config. So remember that. So I could have said no IP OSPF priority 2, or I could set it to 1. In both cases, I'm going to get exactly what I was looking for, which is the priority value is gone here. It's back to the default. Now, we've done this on router A, router B, and router C. We're at 100% right now, but we've got one last thing to do, and that's we need to start with router A, and we're going to clear the IP OSPF process. Now, this resets the OSPF process. It's done from privilege exec. Clear IP OSPF proc. It's going to prompt me and say, are you sure you want to do this? Now, to be clear, this is not a command that you're running in your production network during the day, right? This would become what I like to call a resume generating event, which means you'll be updating your resume after you do this in your production environment if it's not a scheduled outage, because this is going to take your OSPF environment down. Now, I need to quickly scurry over here, clear IP OSPF proc, to router B and to router C, and I'm going to explain why that is. Clear IP OSPF proc, proc, yes. Now, the reason I had to quickly move to each of these routers as fast as I could is that, remember, the OSPF DR BDR election process is not a process that goes on forever. And what that means is it's going to last approximately, and I'm going to say right around 40 to 45 seconds before the routers either determine that, hey, there's nobody else here, I'm going to be the DR, or the DR and the BDR have been selected. And so I needed to quickly reset each of those to make sure that we end up with the right result before the election ran and finished on its own, right? Which may give me something that I'm not looking for. So let's go ahead and take a look now. And we've got these great commands, show IP OSPF neighbor. And we can see, as we would expect, the BDR with the second highest priority, router B, and then the druther is router C. If we look at router B and we go ahead and say show IP OSPF neighbor, we see that the designated router is router A. We see that the the druther is router C. And then finally, router C, and you can see we're fully adjacent with everybody here, right? So let's say show IP OSPF neighbor. And router C, who's the druther, sees router A as the DR and router B as the BDR. So this is a great exercise, right? It gets us to understand that the process is not preemptive. Once your DR and BDR have been selected, unless one of them goes down, they will remain as the DR and the BDR. So from a network design perspective, this is a great reason as to why you want to make sure you pick some pretty beefy and redundant routers or multi-layer switches, which are really just routers disguised as a switch. Make sure that they are beefy and redundant power supplies, redundant supervisors, because you want to maintain continuity and consistency in your environment, because it's all about OSPF, the link state database, and the link state advertisements that are floating around that network that are the responsibility of the designated router to communicate to all other routers. Now, the final thing I'm going to do here is I'm going to grab a 2901 router. It's locked. All right. Well, what I was going to do was add a router in here to see that the state of the druthers with each other goes to a two-way state. And actually, I've got some routers here. We can quickly do that right now. So let me go ahead and pull router 1 up. I'm going to go and say router OSPF 1, and we're going to set the router ID to 0001, and I'm going to just use that network statement I briefly touched on in my previous network tutorial, or packet tracer tutorial, and that's at quad zeros, and that's going to activate OSPF on all interfaces. Router OSPF 1, and we're going to set the router ID here to 0002, and then I'm going to use that network quad zeros, area, sorry, left out one of the zeros, area 0, and then we're going to come over here to router 3. We're going to do the same thing. And again, these routers are all connected over Ethernet interfaces. We'll go into global config, router OSPF 1. We'll set the router ID here to 0003, and then we'll use that network quad zeros command. Again, very quick and dirty way in a lab environment. This is exactly what I said you would use this for, and this is exactly what we're using it for now. And let's see, router 9 and router 10, what are we doing here? Or router 8 and router 9, so here we go. Router 9, we're going to go into global config. We'll say router OSPF 1. We'll say router ID 0009. And we need 4 routers in order to see that we're going to have 2 that will be in the two-way state, and they're going to be our druthers. They are not fully adjacent with anybody else. All right, so I brought those online rather quickly. The router IDs go from lowest right here with router 1 to the highest, which is router 9. And let me say, do show IP interface brief. Let's make sure that I can ping 10.0.0.1. And do I have connectivity to 2? I do. And what about the 3? Just making sure that router 9 is going to participate here. Do show run section router OSPF. All right, there we go. So do show IP OSPF neighbor, and it might take a few seconds here, and yes, it is taking, there we go. And of course, right on cue, as I'm starting to panic, OSPF a little longer for the finite state machine to get to the fully adjacent state. But let's take a look here and see what we've got. You can see that if I was to say do show IP OSPF interface for the fast Ethernet 00, which is the interface I've got configured here, you can see that who is the designated router? Well, it's me, router 9, because I have the highest OSPF router ID. We didn't work with the OSPF priorities. Remember, OSPF priority, that's the #1 indicator, followed by #2 being the router ID, because the router ID is a great tiebreaker. It's the fingerprint. It's globally unique in the OSPF routing domain here. Now, that would mean that router 1 did not become the DR or the BDR. Let's see what show IP OSPF interface gigabit Ethernet 00 on this 3945 here. So it sees router 9 as the DR. It sees router 3 as the BDR. So if I say show IP OSPF neighbor, here is what I was trying to get to, which is router 1 and router 2. They have the lowest router IDs. They are not the DR and they are not the BDR. Remember, router 3 is the backup designated router. Router 9 is the designated router. And you can see the default priorities that are listed here. And this is a serial interface, which is why the priority is 0 on the serial interface, because there is no DR BDR. Now, for router 3 and router 2 over this fast Ethernet interface, you can see they're in a two-way state. They do not become fully adjacent with each other. This is all about that n times n-1 divided by 2. Router 2 and router 1 know about each other. They're in the two-way state, so they see each other from an OSPF perspective. But they will not transition to fully adjacent, and they will be druthers, just DR other. It's something other than the DR or the BDR. And so I just wanted to show you that real quickly because the activity didn't allow me to make the modification, and that's a very important point. So let's go ahead, let's take a step back, and let's review. That is going to do it for this video, but a few things that are going to be very, very important to remember. Remember that on a broadcast multi-access segment like Ethernet, we have a DR BDR election. The default OSPF priority is 1. We can set it with the IP OSPF priority command on the interface that's participating in that multi-access broadcast domain. Remember, on a point-to-point link, There is no DR BDR because the DR and the BDR are the only two things on that segment based off the definition of point to point. The addresses 224.0.0.5 and 224.0.0.6. Very, very important addresses to know. 224.0.0.5, the all OSPF routers address. That's going to go to anybody that's listening and running the OSPF process on their interface. And then you've got 224.0.0.6. That is the address to which all other routers, the DROTHERS, are going to be sending their link state advertisements to, because it's going to go to the DR and the BDR, because 224.0.0.6 is the all DRs address, the backup designated router and the primary designated router. And it's only the designated router that's responsible for then taking those LSAs and shipping them out to everybody on the 224.0.0.5. It's all about scalability with the DR and the BDR. Remember, we talked about the John T. Moy book. We saw that Moy said, hey, I see that the IS to IS routing protocol and the OSI stack, they're using what's called a pseudonode. And that's a great way to do it. So I'm going to adopt that method and borrow their hard work and implement it, and I'm going to call it the designated router, and we're going to have a backup designated router. And very important, we saw that the DR and the BDR are not preempted once they are elected, and that finite state machine has finished that election for the DR and the BDR. They are going to stay the DR and the BDR until a disruptive event takes place, even when we're bringing routers online with superior OSPF priorities set on their interfaces, or if the priorities aren't set, superior router IDs in OSPF. All right, well, that is going to do it for this video. Again, I really hope I've earned your time here by explaining the DR and the BDR. You're going to see a pop-up window shortly that's going to take you to the next packet tracer activity that's part of the new Cisco Networking Academy Enterprise Networking Security and Automation CCNAv7 curriculum. Thank you so much for watching. Have a great and safe holiday, and I will see you in the next video.